Welcome back to ECE 320A. It is Pi Day if you are paying attention to the date, but it's 3/14 in 2019. You might want to go get a pie tonight just to celebrate. That's my excuse. Probably won't get one, but I can always dream. If you're dreaming, don't forget you have an exam next week and you have a homework assignment. The homework assignment is due next Tuesday. That's homework number 5. And the exam is a week from today. And in between your due date for homework number 5 and the exam number 2 is an information session on technical electives for next academic year, fall and spring. And if you're interested in the Accelerated Master's program, a little information on that. And that will be held Wednesday afternoon at 4 o'clock in ECE 530. We will, according to the vote that was taken in class last time, we will have a review session in here. Hopefully it will be in here. I'll try to let you know if that changes, but for now we're planning on next Tuesday at 5 o'clock having a review session for exam number 2. And if you have questions that you would like to see addressed during that review session, there is a quiz in D2L. It's not for points, but it's for you to type in, oh, I'm having trouble with this concept, or I would like to see this problem worked on some previous exams or practice exams, which you can find in another module in D2L. It's the exam number 2 module. And you should be able to sit down and work out many practice exams, and the answers are there if you get stumped. Hopefully that will get us ready for exam number 2. To continue getting us ready, we want to pick up with what we haven't yet covered, which concerns case number 2 of the inverse Laplace transforms. We will quickly review what I actually added into the notes after Tuesday's class on the distinct roots case. Today, we'll then jump into case number 2, which is repeated roots. And when you have repeated roots, here are 2 formulas or expressions that you'll want to be very comfortable with. And if it doesn't look clean, you need to make sure it looks clean or you understand how to apply it before exam number 2. And there's 2 different relationships. They're basically like 2 different rows in your Laplace transform table. One is when you have a real root or a real pole at s equal minus a, and the other case is when you have complex conjugate poles that are repeated. Repeated means that you just have a bunch of them on top of each other. In the first case with real, maybe you have 4 poles at s equal to minus 5. Then you would have to use this particular strategy for all 5 of the different partial fraction expansion terms you have associated with that factor s plus 5 to the, what did I say? How many times was it repeated? 4 times? Or however many times it's repeated. Here it's repeated n, as in Nevada, times. So whatever n is, then you can, in the time domain, write down, based on what your coefficient is in the partial fraction expansion, which is labeled as a here, you now divide that by n minus 1 factorial t raised to a power of n minus 1. And then we also have these exponentials. The exponential you would expect. Anytime you have a real pole at, let's say, minus 5, you have an e to the minus 5t. But if that now starts getting repeated, you have powers of t to make these modes linearly independent. You have an e to the minus 5t, then you would have a t e to the minus 5t. Then you would have a t squared e to the minus 5t, depending on how many times that mode is, or that pole is repeated in your partial fraction expansion. It gets even more interesting when you have repeated complex poles. And that's what I'm trying to illustrate here. In the second row, it actually takes two lines on the computer screen to combine the conjugate pole pairs. But again, you have a pole that's repeated n times. And if you don't have time to write this down, you can get access to this on D2L, and in the textbook, the 11th edition, it's Formula 11 and 12 in Chapter 12. So these are there. Maybe they use R instead of N, but I kind of like N instead of R. But R is just an index or an integer representing the number of times that particular pole or pole pair is repeated. But you definitely need to make sure that you understand this so that you can solve the homework problems, because sometimes they have a magic number that you have to divide by. If it's repeated 3 times, then you have 3 minus 1, which is 2, factorial, which is 2. Meaning you're dividing your constant a by 2, and then say, oh, it's t squared e to the minus, let's say, 5t. We'll go through some examples today using these strategies, because I'm still in the goals portion of today. I haven't started lecturing, or we haven't started interacting officially. Table 12.3 documents 2 such conditions for both real and complex. So you see 4 useful transform pairs in table 12.3. The 4 is because you're only looking at a single pole, and then it's repeated twice for both the real case and the complex case. If you want to see it in just those cases, n equal 1 and n equal 2, that's provided in table 12.3. When we have repeated roots, the cover-up method falls apart when we're trying to find these partial fraction expansion coefficients. And that's why we're going to talk about different ways or multiple techniques for computing these numerator coefficients. That's why we're talking about this, is because when we have repeated roots, boom, something just happened, and we no longer can use the cover-up method to find all of these coefficients in our numerators. We can find the coefficient on top of the highest power of the repeated pole, but the others, we need some other way of doing it, and that's why we're talking about these multiple techniques. And you pick your favorite one. I'm going to show you about 4. Hopefully we'll have time. And you decide which strategy, or you say, oh, in this case, I'm going to use strategy A. In this case, no, I think strategy C is better. Or in this case, maybe strategy 4 is better. It's up to you. But whatever way you pick, you need to pick something instead of the cover-up method that we've been emphasizing with case 1, which is distinct poles. Wow. I hope no one had anything else to do today. We'll be here for another 8 hours. We're going to be talking about poles and zeros of transfer functions, final value theorem, initial value theorem, and this idea of, wait a minute, I'm used to having k over a complex pole pair representation. What in the world is Tharp doing? He's got complex roots, but he doesn't have complex numbers in the denominator. The relationship, or why those are consistent, meaning why is it that these two equations are equivalent? Here is a exponentially damped cosine plus an exponentially damped sine, some linear combination of those. Well, that's equivalent to having a phase shifted cosine that's exponentially damped. Do you see the common terms in those two expressions? Well, how is it shaking? It's shaking by beta, and that's the imaginary component of the complex root. It's not changing the way it's shaking. in either way. What else is the same? The exponential decay, the alpha. How far into the left half plane are we? That didn't change with our poles, and it doesn't change in these equivalent relationships. What does change is now we've collapsed a sine and cosine that's damped the same and at the same frequency into just one cosine. Or you could have done it into a sine, but the convention is let's just work with cosines. And this is just a phase shifted, and you could just think of that as having a time lag or a time advance. That's what a phase shift really corresponds to, if we were to factor this beta out of that angle. And here's another point that might cause confusion if somebody ever asks you to compute numerically what this expression equals at some fixed time. Beta, we usually think of that as the omega, the vertical distance in the complex plane. That's the imaginary component of our complex poles. It has units of usually radians per second. T, units of seconds. Here's the hard part. Beta times t has units of radians, and typically we write this angle in degrees. Well, if you start adding radians and degrees, you're going to get a mess. And then you try to take the cosine of that. So make sure that these two terms in your argument of the cosine are consistent, either radians or degrees. So you convert one back to the other, and make sure your calculator knows what you have in the argument. If your calculator's set up to be taking the cosine of angles in degrees, don't have this argument in radians, or vice versa. If you have your calculator set up to be taking the cosine of an angle that's measured in radians, make sure both of those are now in radians. Is that clear? And what we don't get to, I might provide in D2L after class. I won't force you to stay here and listen to me for another 8 hours. I'll just let you watch it for 8 hours. How's that? Yes, question. What's the relationship between A, B, and C, the weights or the amounts of the cosine and sine to get down to this cosine? It's really in a quick, I'm not trying to be cute, but kind of, it's really Pythagorean. So A and B and C are like the hypotenuse of a right triangle, where A and B are the sides of a right triangle. And theta is really sort of this angle determined by A and B. B is the vertical component. A is the horizontal component. We can kind of draw this cosine and sine in orthogonal directions. And now we say, oh, what's the angle associated with how much sine we have and how much cosine we have? And what's the magnitude of that cosine? Well, that's the hypotenuse associated with A and B. That will be discussed when we talk about this equivalence. But in sort of, if you're trying to see this, you would say A, B, and C. I've now learned my ABCs again, but it's relative to Pythagorean, a right triangle. So it's really not that, what do I want to say, difficult, but you kind of have to keep track of it. But really it's just A, B, and C, or A and B create C and theta, or vice versa. Yes?
The beta from below is the same as the beta from the top?
So the question is, are the alphas and the betas, I didn't mess up there. The alphas and the betas are consistent in the bottom entry as they are in the top. So the exponential decay is the same. If these are equivalent, they better give me exactly the same curve or waveform on the time axis. That's what I'm saying by their equivalent. And sometimes it's easier to see, to visualize this one cosine that's exponentially damped versus, wait a minute, I have an exponentially damped cosine, I have an exponentially damped sine. You want me to draw both of those and then add them up? Well, that's what the top one says, but the bottom one says you have one that's shifted in time, but it's just an exponentially damped cosine. And that's what the cosine and sine produce together. They're equivalent. It's kind of neat, actually, and it starts to make sense, I hope, before exam number 2. Here's what we talked about from before. This is the last time we were together. You've probably forgotten, or maybe you weren't here before. Oh, you missed a great. But here we have this example. Is this example, can I immediately start doing a partial fraction expansion? And why am I asking that question? It needs to be strictly proper, doesn't it? The denominator order has to exceed the numerator order, and it does. It's a cubic downstairs, and it's a quadratic upstairs. We can now write that, and we did last time. I'm now skipping over what we talked about last time. Here's what we went through last time. Did everyone have their Dramamine before class? Wow, really? Here we go. So this is what we did last time, motion sickness for Dramamine. Anyway, here's f of s, and we wrote that as 3 terms. First we found the roots. We showed that one was real and one was complex, and then we looked at putting these over the 3 distinct roots. It's critical to understand that a sub 2, that particular coefficient, is associated with this pole in the second quadrant, or in the upper half of the complex S-plane. That's critical. Don't forget that. And A2 and A3, they're complex conjugates of each other. You just have to find A1, which we can do with the cover-up. We can also find A2 by the cover-up because these are distinct poles. Doing that then allows us to write in polar form. The a sub 2 and the a sub 3 are just complex numbers, and I've written them in polar form in this case. And now do you see how I immediately went from the partial fraction expansion equation into the time domain? I know that 1 over s plus 1 gives me an e to the minus t. And it's scaled by the a sub 1, which is 1/2. The time domain expression associated with complex roots, anytime you see complex roots, you need to immediately think exponentially damped sines and cosines. In this case, and it's shown in, and I provided notes after class for last time. So you can find how this arises, but we have 2 times the magnitude of that coefficient. E to the minus 2t, that's due to the real part of the complex pole. The shaking, the omega, how far away it is from or its imaginary component, 3, is what it's shaking with, cosine of 3t, and then the phase shift comes from the angle associated with a sub 2. If a sub 2's angle ended up being minus 20, you would put minus 20 into your time domain response. It's not always going to be positive. Doesn't have to be. Is that clear? Whatever results for a sub 2, and where was a sub 2? A sub 2 was the partial fraction expansion coefficient associated with that pole that was in the upper half of the complex S-plane at s equal to minus 2 plus J3. That's the value of s that causes this denominator to vanish. There's a lot to keep track of, but it's important to keep track of that. Yes? Who was?
Yeah. So I want to make sure that the denominator has the root or the pole that goes in the
Yes, so what you want to do is you need to make sure that when you do the cover-up method, you find the partial fraction expansion coefficient. The question was, what factor do I focus on when I'm trying to find my partial fraction expansion coefficient? It's the factor associated with the pole that's in the upper half of the complex S-plane. And you can see that that's this middle term because s equal to minus 2 plus j3 causes that term to vanish. When you solve for that coefficient, here it's 1.1 at an angle of 51 degrees. That's the one that you use in the time domain equation. And that's for real distinct roots. Put on your seatbelt when we get to repeated roots. And yes, shoulder harness, maybe even a hard hat or a roll cage, helmet. This was last time. So here is the advertisement. See the notes appended to the previous lecture. We didn't go over that in class, but I did write it down after class. If you want to know, wait a minute, he seemed to be just talking hot air. Well, maybe, but you need to understand it, and it's now laid out for you in the notes appended to the previous lecture. How to get from capital F of S to lowercase f of t. Inverse Laplace transforming. Let's now look at what happens when we go into repeated roots. What do I mean by repeated roots? I hope it's clear. Here's some numerator polynomial, and I haven't specified it, over s plus p sub 1 squared, s plus p sub 3. And so I've lost p sub 2, but I have 2 poles at p sub 1. So that's kind of where p sub 2 went, if you're wondering. Doesn't matter. You can label these however you want. But what am I assuming if I've now written that right-hand side? What have I assumed is true? That it's strictly proper. That n sub 2 of s is actually a polynomial that's second order, first order, or constant. That I've assumed. But what have I done? I now have to include not only this factor that has s plus p1 squared, but I have to keep decreasing that power that that's raised to until I run out of factors, or until I hit s plus p sub 1 raised to the first factor. I start with the highest one. Here it's just 2, and then I go, okay, I need another one, a sub 2 over s plus p1. Oh, I'm done. I can now go on to the other factors, which in this case is just one more factor, s plus p sub 3. It's third order, and I have 3 terms in my partial fraction expansion. I now need to find a1, a2, and a sub 3. a1 and a3 we can find like we did before for distinct poles. A sub 2, that's where we end up with trouble. That's what I'm saying here. We can find a sub 3 using the standard cover-up method. Multiply all terms by this factor s plus p sub 3. Then the left-hand side of the black equation upstairs loses the s plus p sub 3 factor, and we evaluate then n sub 2 over s divided by s plus p1 squared at the value of s that causes that s plus p sub 3 value factor to vanish, which is when s is equal to minus p sub 3. And that's what a sub 3 equals. A1, which was the partial fraction expansion coefficient over the highest power of that factor, we can also find using the cover-up method. We multiply all terms by s plus p sub 1 squared. That now leaves us with n sub 2 over s plus p sub 3, and we evaluate that at s equal to minus p sub 1, and that's what a sub 1 will equal. We now have a sub 1 and a sub 2 determined, and this is where we want to sort of spend our time today, is how do we now find a sub 2? A sub 2 arises because we had repeated roots. You can use these additional techniques when you have distinct roots if you want, but you definitely need to use them when you have repeated roots. But you could use them anytime you wanted to find a partial fraction expansion. And what we will do is we'll go ahead and assume that we've already calculated in this example a sub 1 and a sub 3. We found those using the cover-up method. We have three unknowns, a1, a2, and a3. And once we have those, we can go into the time domain because we have the expressions to do that. Let's look at a particular example. Suppose now we are given f of s equaling 2s plus 1, that's the numerator, over s plus 1 squared times s plus 2. And if I ask you to write down the right-hand side, that should just be automatic. Once you see this, or first, what's your first check? Make sure it's strictly proper, and it is. We have a linear factor upstairs and a cubic downstairs. Now we can say, oh, I have a repeated pole at s equal to minus 1. I need to start with that, s plus 1 squared, and then I go, I have another one because I can reduce that exponent. I have a sub 2 over s plus 1. Okay, I'm down to power of 1 on that repeated factor. I can stop. I have two partial fraction expansion terms associated with that root that's repeated twice, and then I can include a third partial fraction expansion term associated with the third factor. A sub 3 over s plus 2. That we should be comfortable with. Then, if I simply said, what's the structure of your time domain expression, you can actually now write that down. And which pieces go with what parts? Meaning, once you see this 2, you say, oh, what mode, and here I'm going to do this, but it's really a decay, isn't it? Because it's a real factor. Now I know what my mode is associated with that pole. I have a mode, exponential decay, of e to the minus 2t. That's the value of s that causes that last term to vanish. That 2 then says, oh, there's my mode, e to the minus 2t. The 1 right here, you can't see it, but it's minus 1t, and 1 we typically don't write, so we just say e to the minus t, but that 1 right there is the mode associated with that term, a sub 2 over s plus 1. The repeated pieces get a little bit more interesting. This 1, again, gives us a minus 1 right there. But since it's repeated, we need the additional term to be independent of this a sub 2 e to the minus t. To get it independent, we need to start multiplying it by polynomials of t, or powers of t. And the first power is t. If we needed another one, if it was repeated 3 times, we would have a t squared. If it was repeated a 4th time, we would have a t cubed that weights e to the minus t. It's always going to weight e to the minus t if our pole is at minus 1. What I'm saying is this 2 gives rise to that t. And there's where all the pieces and parts go together. If you now have A1, A2, and A3, if you were short on time and you've now found this or written down this partial fraction expansion on the exam, you could immediately start to write down its time domain version. And you could say, okay, if I have time, I'll go back and find A1, A2, and A3. And then it's just a matter of plugging those into those weights or coefficients in our time domain waveform. Where did that come from? I already showed you this in the marketing or the advertisement, the commercial, in our goals part of today's class. This comes from equation 12.11. You plug in little n equal to 2, and you'll see that we get t raised to what power? 2 minus 1, or t to the 1. So there gives us our t to the 1 power. What are we dividing our coefficient by? If n is 2, it's 2 minus 1. 1 factorial is 1. Oh, we didn't have to divide by. Well, yes, we didn't have to divide by anything. It just fell out. But you start getting n equal to 3, then you have to worry about dividing those partial fraction expansion coefficients with numbers to get the correct answer. Let's do it. Now I am doing a commercial. That was a Nike commercial. Just do it. But maybe that's too far in the past. You probably weren't even born when that was the marketing strategy. Are they still using it? Just do it. So let's just do it. Let's just do it. Let's find these coefficients. Which one do we want to just do now? And if you were pressed for time, which one would you maybe start? Which ones would you start with? Okay, so you don't know which one, or maybe you all want to start with the hardest one first. I would do A2. That's the hardest one. A1 and A3 are the easy ones. I'm going to do the easy ones so I can get my momentum going. If I'm just doing it, need to build some momentum. Let's start with A sub 3. A sub 3, what in the world? It's not wanting to just do anything. A sub 3 is using the cover-up method. I have to cover up the s plus 2 factor on the left-hand side. Or I have 2s plus 1 over s plus 1 squared. And where do I evaluate it? What value of s? I've evaluated at the value of s that causes that denominator factor under a sub 3 to vanish. So that's now at s equal to minus 2. Or I now have minus 4 plus 1, or minus 3 divided by 1 squared, minus 1 squared, or minus 3. I now have one of my coefficients. The next one that's straightforward, using the cover-up, is to find the coefficient associated with the highest power of my repeated pole pair, or my repeated pole factor. And that's a sub 1. A sub 1 is now 2 s plus 1, same numerator, over s plus 2 now, evaluated at s equal to minus 1. I now have a sub 1 and a sub 3 determined. A sub 2 is the more challenging numerator coefficient to find. If I now multiply through by s plus 1 and try to use the cover-up method, what happens? If I just fell asleep during lecture, then you'll miss it, right? But you won't miss it on the exam. Here, if you multiply through by s plus 1, then you have some terms that still contain in the denominator an s plus 1, and you said s equal to minus 1, you're going to have infinity equals infinity. How do you find anything in that infinite space? It doesn't tell you anything. That's why we have to do something different. That's why we have different strategies for finding a sub 2. So let's look at the first strategy. Suppose the first strategy is we're going to find a2. And this one I'm going to find a sub 2 by selecting. The partial fraction expansion is valid for all values of s. So let me pick a convenient value for s. And that's my only unknown in that equation if I know a1 and a3. The first strategy then to find a sub 2 is going to be to select a convenient value for s. What's convenient? Something other than minus 1 and minus 2. We can't do that because that would just, again, give us infinity equals infinity. An easy one might be just let s equal to 0. That's a convenient one here, because then a lot of these variables just disappear. So let's now just let s equal to 0 in the partial fraction expansion, and now we have 2 times 0 plus 1, that's the numerator, over 0 plus 1. I haven't multiplied through by anything. And I now have my original partial fraction expansion left-hand side. My right-hand side is a1, which I found to be minus 1, 0 plus 1 squared, plus a sub 2 over 0 plus 1, plus a minus 3, or a sub 3, over 0 plus 2. Now I have one equation in the one unknown a sub 2, and I can solve that. This now gives me, on the left-hand side, 1 over 2. I have 1/2 on the left. The first factor gives me minus 1. The second one is a sub 2, and then I have minus 3/2. I add all of those pieces together. I have minus 5/2 on the right. I can add 5/2 to both sides, and I have 5/2 plus 1/2, or 6/2, or 3. That's what a sub 2 is equal to. Now I can write down what f of t is. F of t is a1, which was minus 1, t since it was associated with the repeated pole, minus t. A sub 2 was 3, e to the minus t, and then we had a sub 3, e to the minus 2t, and that's true for t greater than or equal to 0. I now have two terms, two modes in my time domain waveform associated with that repeated mode or pole at minus 1. One of the modes is e to the minus t, the other one is t e to the minus t. That's one strategy, picking or putting in a convenient value of s. If you had more pole, or your pole was repeated more times than twice, you might have to pick more convenient values of s. You might have to pick s equal to 0, s equal to plus 1. That's okay. S equal to 2. Picking integer values for these might be clean or cleaner. Let's do one that everybody likes, the limiting expression. No? But you'll learn to like this one. What am I doing? Limiting A2. I don't want to limit A2 to anything. I want to wake up and say I'm finding A sub 2 using a limiting expression argument. The strategy is to first multiply all my terms, or multiply both sides by s. Then I want to take the limit on all terms, take the limit of the left side and the right side as s goes off to infinity. Let s grow, and then see what happens, or that now allows me to solve for a sub 2. Let's do that in this example. We had 2s plus 1 over s plus 1 squared s plus 2. And the very first step, we said multiply both sides by s, so I need to multiply that by s. Let me try to emphasize that. Can you see the different colors? So here's blue, s, and then the other was what we started with. And we have our a1 over s plus 1 squared plus a sub 2 over s plus 1 plus a sub 3 over s plus 2. I was going to say squared, but we didn't have that one repeated, did we? And we now need to multiply all of those by s. If we do something to one side, we have to do the same thing to the other side. And we already know that a1 was minus 1, a sub 3 was minus 3. Now can I sort of do the following? Can I just down here say what happens as s goes off to infinity? That's what I'm doing now. What happens to this left hand side of the equality when I let s go off to infinity? Well, the highest power of the numerator in s is going to be divided by the highest power of s in the denominator. The highest power in the numerator is 2s squared. You have to keep track of the 2. It may be important. May. And what's downstairs? S cubed. Now I have 2s squared over s cubed. I can factor that to 2 over s, eliminating the s squared in the numerator and denominator. I had 2s, so I had 2s squared over s cubed. I'm now basically getting rid of, so it looks like 2 over s, and as s goes to infinity, that vanishes, doesn't it? So I'm just going to write that as 0. See how quick this is? To use this limiting expression, you're going to love this. Keep an open mind. What happens to the first term on the right-hand side as s goes to infinity? We have minus s over s squared. We have minus 1 over s, which vanishes as s goes to infinity. You need to be comfortable with where these are coming from. What happens to the middle term as s goes to infinity? We have a2s over s. The s's cancel because they're going to infinity at the same rate, and we're left with a sub 2. And if we didn't have that third term, we would say, oh, a sub 2 actually is 0 from this analysis. But that's not going to be the case, is it? What's our third term? As s goes to infinity, we have minus 3s over s. The s's cancel, and we have minus 3. Or, solving for a sub 2, we have a sub 2 is equal to 3. That better be what we had in the first strategy. These all better, what? You don't remember? I was hoping somebody remembered. Now we feel nice, don't we? Because it is consistent with our first strategy, a convenient value of s. This was a limiting expression strategy. And what else can we do? Well, we can do, like I said, how long do you have? Let's keep going. Let's try another one. We're still finding a sub 2. You would think we found it, and we have. But this strategy, I'm going to say, is the common denominator approach. First step is simply obtaining a common denominator. On the right-hand side. We've done this partial fraction, and now we put it back together. We've separated it out. Now we put it back together. Then what we do is we equate coefficients of like powers of s in the numerator. We're going to have a numerator on the left of the equality sign and a numerator on the right, and we just compare the coefficients on the left side and the right side. That might give us 3 coefficients and 3 unknowns. We know how to solve that. Might give us 4, depending on the power or the order of that numerator polynomial. Step C is to solve those equations. Solve the equations for the unknown coefficients. Again, you can use this even when you have distinct roots if you want to, but it's probably cleaner to do the cover-up. Why? The cover-up allows us to get 1 equation and 1 unknown. So you get 3 independent equations for the 3 unknowns. Here, if we didn't solve for A1 and A3 before, we would have 3 equations in the 3 unknowns. Now you have to invert a 3 by 3 matrix. You're all taking 310. You know how to do that. Piece of cake. Okay. So, How do I know? I have your entire... you won. If you don't know the answer before you ask the question, no. That we're not in law school, are we? So that's what they learn across the street at law school.
They're supposed to know the answers to.
Yes, you want to ask questions that you know the person sitting in that chair is going to give you, or you're going to be in trouble. If he tells you an answer that you didn't expect and it flips, never mind. We're not north of Speedway, are we? No, we're engineers. So here's...
What's the point of already having the answer to the problem? It's not a problem.
Well, they're not dealing with technical problems. They're dealing with people problems, usually, unless you're an expert witness. Let's not get distracted. Okay, here we are again. There's our... Now what do? Well, we get a common denominator on the right-hand side. Like I said, we've just separated all these parts out. Now we put them back together, meaning we put this downstairs. And what happens if we now put that first A1 on top of this denominator? To make it equal. The top line has to equal the bottom line. We have to multiply A1 by S plus 2. What do we multiply A sub 2 by? It now has to include S plus 1 and S plus 2. What about A sub 3? We comfortable with that? Now we've put everything back together, and this is now the relationship between A1, A2, and A3. This we could multiply out. We have S squared plus 3S plus 2, and this one is now S squared plus 2S plus 1. Or the numerator now becomes... what? We start combining what multiplies S squared on the right-hand side. What? Oh. How did that happen? Anybody know a CPR? I'm going to need it shortly. I'm going to have a heart attack. I think we're back where we want it to be, correct? So that's now times S squared. What is my next one? It's all the factors that are scaling S. I see an A1. I see a 3A sub 2. And a 2A sub 3. And finally, I have my coefficient that is associated with S to the 0 power, or the constant. And that's 2A1. Going in here is now 2A1 plus 2A2 plus A sub 3. That's all the numerator. Question? I don't know. Should it be a 3A sub 2? Where were we? A sub 2. What should it be? So now, did I do the algebra correct? I'm just multiplying out the right hand in the blue And now I'm just collecting all of my coefficients for s squared, s, and s to the 0. Once I have that, I now can compare that with my original numerator. Right there. And do I have an s squared?
0.
It's 0. I have 0 times s squared. Whatever my coefficient was that scaled s sub 2 or s squared on the right is going to be set equal to 0. Likewise for the s1 coefficient and the s to the 0 coefficient. That's what I'm meaning when I say over here, if I now say equate coefficients, I now have my s squared coefficient, I have my s to the 1 coefficients, and I have my s to the 0 coefficients. This one you just said the left-hand side was 0, and on the right-hand side that was the sum of a sub 2 and a sub 3. Or I now know that a sub 2 is equal to minus a sub 3. And I would be done if I've already found a sub 3 and a sub 1 using the cover-up method, and I wouldn't have to keep going. I could just look at one of these coefficients and be done. But if you haven't done that and you wanted to see, oh, is my algebra correct? We had 2 on the left, and that was equal to a1 plus 3a sub 2 plus 2a sub 2. And finally, the constant coefficient was 1 on the left, and on the right, 2a1 plus 2a sub 2 plus a sub 3. You know, this computer is starting to scare me. It must have some artificial intelligence. It's already turned on MATLAB. It knows I want to invert a matrix. My hand must just be, I didn't turn it on tablet mode, so now it's picking up on all the different pushes, and maybe that's why it erased before. Who knows? But I'm not going to invert this matrix. But I can, yes. I don't know, is my printing that bad? Which row are you on? The second row. I have 2 is equal to a1 plus 3a2 plus... I hate to even erase, but you're correct. This should be... Thank you, an a sub 3. Is that better?
Yeah.
Now, if we were in 310, ECE 310, not room 310, I don't know what that room looks like in this building. Don't go running to 310, it's just on the 3rd floor. But it's on... Oh, gosh. All right, how do we put this into a matrix? Yeah.
The first row A1, or the first column A1, the second column A2. No, like the first column is
This is how I'm going to do it. Why'd I ask? So if I did this and I now said, what's my matrix here? That's equal to this. Right? So now my first row, I could say, is A1 plus A3, or I'm sorry, A2 plus A3 equals 0. That's the first equation. The second equation says I equal to 2, and that was A1 plus 3A2 plus 2A sub 3. And finally, it should equal to 1, and this is now 2a1 plus 2a sub 2 plus a sub 3. And now you wondered why you were studying these matrices and linear algebra so you could do circuits in this class. Yes, partial fraction expansion. Yes. So the question was on an exam, am I going to tell you what method you have to use? I'm going to give you maybe a poll. Maybe it'll be complex and it'll be repeated 10 times. And I'll say, use the common denominator approach. And now you have to what? Invert a matrix that has complex numbers in it that might be 20 by 20 if we have no, you can use whatever strategy you want. So you don't have to use the limiting expression if you don't want. But the common denominator, you can see, if we didn't already find A1 and A3, this would be a strategy to use. Might not be your favorite strategy, but it will be a default strategy if you had MATLAB open, which you won't on the exam, but on your homework you could. You could say, let me check. It's not, mastering is not saying this answer is correct. Let me do it a different way. And then you do this and you go, oh, there was my algebra mistake. I put the changed the subscript. If you were to do this, let's say that this is now M and this is B, you would find A is equal to M inverse B, and A1, A2, and A sub 3 better be what we had before, which was -1, 3, and -3. I didn't use MATLAB, but it's open, ready to go, but it's too slow to do without a keyboard. But you can do it. It wasn't supposed to open, but like I said, it's feeling that I wanted it. We have one more strategy for finding A sub 2. Finding A sub 2. Strategy 4. And this is the derivative method. Where did everybody go? Oh, I started talking calculus and everybody disappeared. Well, now I'm in my office by myself. I'm going to do the derivative method. If you want to read this as far as the explanation in words, you can refer to page 466 in the textbook. And this is actually what they call method B. First step in this is to go ahead and multiply by the highest power factor of that repeated root. So multiply through by the highest power of the repeated root factor. Here's everybody's favorite step, is to differentiate with respect to x, with respect to s. So differentiate with respect to s. Once you've done that, then you evaluate the result at the root location. And then finally you solve for the unknown coefficient, which in our case is A sub 2. Let's try that for our example. Step A is we multiply through by why am I doing it in terms of unknowns? Let's see if I can do it for specific values. Can I? Not without doing another example. All right, so this is going to get scary. What do we have? S. Well, let's do it in terms of unknowns, and then we can plug ours in that we had before. So we had For example, s plus p1 squared times f of s. So in terms of what we've done, a1 was on top of s plus p1 squared, so we now cancel it. What did we have before? We have a sub 2 sitting on top of s plus p1, and we're multiplying by s plus p1 squared. This now has an s plus p1 sitting, or multiplying by it. Then we have a sub 3 s plus p1 squared over s plus p sub 3. I'm doing it in general so that you can see what actually happens in the different steps. We're okay with this line. We just multiplied both sides through by the highest power of our repeated pole factor. And we have s plus p1 squared times the original transform, and then a1, a2, and a sub 3 terms are what have resulted. What now happens when we start differentiating? Now we differentiate with respect to s. This s plus p1 squared f of s, and I'm actually going to evaluate this in step 3. So do I want, let's just do it here for now. Let's just write it that way. Okay, I've now differentiated this, which I'm not going to do formally, but that's what I have. What happens when I differentiate a sub 1 on the right with respect to s? I don't get anything, do I? Well, I get 0. What happens when I differentiate a sub 2 times s plus p1 with respect to s? Oh, that's looking promising. That's really what I wanted, wasn't it? To somehow isolate a sub 2. And what happens when I do the next term? You use your favorite strategy to take the derivative of a ratio or a quotient, right? Let me just write down what I did. I did the derivative of the numerator. So I now have 2 a sub 3 s plus p1, and then I differentiate what was in s plus p1 with respect to s, which is derivative of s, and that's 1, all over the denominator, s plus p sub 3, plus, or really it'll be minus, because I'm differentiating, or I'm doing the denominator, and that will raise that to one higher power. And I have a sub 3 s plus p1 squared. Now, the next step in this process was to evaluate terms at s equal minus p sub 1. Meaning, now I go back up here and I plug in s equal to minus p1. I plug in s equal to minus p1. I plug in s equal minus p1. And what happens to those last two terms? They were ugly, but when I evaluate them at s equal to minus p1, do you see what happens to those two terms? They're gone. And on the right-hand side, all I'm left with is a sub 2. Meaning, now I have a sub 2 is equal to whatever I started with. And what's this s plus p1 squared f of s? It's not that involved, is it? So that now I actually have, in step D, I now have a sub 2 is equal to d by ds s plus p1 squared f of s evaluated at s equal to minus p1. But this was now d by ds of what I had in f sub 2 in general was n sub 2. I've now canceled that biggest s plus p1 factor downstairs squared, and I'm just left with s plus p sub 3. So what I'm differentiating is not as complicated as the original expression because I've canceled the mess associated with the repeated pole factor. And in general, you can do this for all of the, if you had a higher power of repeated roots, you could do this for all of those different powers. You would multiply through by the highest power and then just keep differentiating. Meaning, eventually, let me write down in general. Does the argument for what we're doing make sense? Sort of, no. Do it for one. Maybe you'll never do it again, but you might want to see what happens when you do it for one. But in general, what's going to happen for an nth order root, let's say in general for an nth order root, we have now f of s is equal to n of s over, let's say s plus, let's just say we have one root and it's repeated n times. Then we would have a1 over s plus p sub 0 to the n plus a sub 2 s plus p sub 0 to the n minus 1. And I would just keep going until I had a sub n over s plus p sub 0 to the first power. Using that formula, then I would find that each of these partial fraction expansion coefficients, a sub l, are equal to the following. 1 over L minus 1 factorial. Because I'm repeating this so many times, then I'm differentiating L minus 1 ds of L minus 1, s plus p sub 0 to the n, f of s. And I evaluate that at s equal to minus p sub 0, and I can do that for all of these different l's, all the way up to n. The formula looks ugly, but the process is you just keep differentiating. Meaning, if you wanted a sub 1, what is a sub 1? A sub 1 is the coefficient on top of the highest power of that repeated pole. And what comes out here? Well, you would have 1 divided by, if L is equal to 1, 0 factorial, which thankfully is just 1. Then how much do you differentiate? You don't differentiate, do you? You've just multiplied by s plus p0 to the n times f of s and evaluated at that pole. That defaults to our cover-up method. Well, you want 2 if you had it repeated twice, or let's say you had it repeated 10 times. The second one, a sub 2, you would be differentiating once. The third power, a sub 3, you would be differentiating twice. But once you've differentiated once, you just keep that result and then differentiate it again, and you just keep going. Questions on that? Do you want me to include one more example in the notes after class? You're not going to stay here with me, I'm sure. I'll probably have another set of class students come in. But I'm going to post material on the final value theorem and the initial value theorem online so that you can do that or use that for your homework before it's due, which is it's due next Tuesday. So look for some additional material on the website.